we're going to go ahead and look at the major types of chemical reactions and their identifying characteristics. So we're first going to start with synthesis reactions. Okay, so your synthesis reaction, or sometimes called a combination reaction, is going to be characterized by the taking of simpler reactants to make a single product. Okay, so if we look at this chemical reaction here, we have elemental sodium, diatomic chlorine, and a single product, sodium chloride. Okay, so your synthesis or combination reactions are characterized by that one product. Decomposition is just basically the breakdown of a more complicated substance into simpler pieces. Okay, and it's the reverse of synthesis. Okay, so what we'll look at here is, notice we have one reactant, okay, and then we have multiple products that are in simpler form. So in this case, in their elemental form. So what we're looking for in decomposition reactions is a single reactant as the defining feature. Okay. Now, single replacement and double replacement, sometimes called displacement reactions, are going to be characterized by the swapping of places of specific elements. So in the case of a single replacement reaction, you're going to have a starting compound that is going to interact with something in its elemental form. And what's going to happen is there is going to be a swap of one of the elements in the compound for that element. Basically like a dance partner cutting in. Okay, now what that will end up producing is a new compound and a new element. Okay, so in single replacement reactions, we're going to have usually something in its elemental form, and then a compound, and then a new compound and new element. In double replacement reactions, we're actually going to start with two compounds. Those compounds are then going to swap partners and produce two new compounds. Okay, now if we look at this, I want you guys to notice that it's very similar to the single replacement. It's just that instead of starting with something in its elemental form and a compound, we have two compounds that we start with and then two new compounds that we produce. Now, in your double replacement or double displacement reactions, you also have the need to produce a product that is not going to be in its ion form. It's not going to be soluble in the solution. Okay, and that's where your solubility rules come in, right? So one of these two products must be insoluble, meaning that it does not dissolve in the water, that it will form a solid, or some sort of substance that is not going to be distributed in the solution. It's not going to be aqueous, okay? So if we look at this, guys, the way we can use a solubility chart real quick, remember, we can find one of our ions. So we have chloride ions. Find the chloride ion here. It says typically form soluble ionic compounds. Okay, now the exceptions to this are if it's combined with silver, mercury, or lead. Okay, and in this case, this is with Pb, which is lead. Okay, so this is going to form our solid precipitate. Okay, if we check the sodium nitrate over here, we look at nitrate, compounds containing nitrate. None of them are going to be insoluble, so this is going to stay aqueous. But this process will occur because we do form that precipitate. Okay. Now, this last example here that we've talked about in the past is combustion. Okay, and obviously a flame is going to be involved in this. And in most chemistry classes in the high school level, we typically kind of simplify it and say, hey, combustion is going to be a hydrocarbon and oxygen, and they're always going to give you CO2 and H2O. Now, the burning of a hydrocarbon is always going to give you CO2 and H2O if it goes to completion. Okay, but with IB, we need to think about this in a broader sense. Okay, so technically speaking, any substance, a metal, a non-metal, hydrocarbon, alcohol, whatever, that reacts with oxygen when heated is going to technically be a combustion reaction. So that means some of the reactions that you've seen in the past that you may have defined as like synthesis might actually be both combustion and synthesis, depending on the situation. Okay, so these are the 5 main types that everybody should be familiar with. The other types of reactions that we'll be talking about in the near future are redox, okay, neutralization, and then a myriad of organic reactions that we will discuss. Okay, now again, there may be overlap in some of these main definitions that you guys are probably familiar with, but we will expand upon that as we proceed. Okay, so let's go ahead and let's utilize some of our skills. Okay, so combustion reactions, remember, it's when we heat a substance with oxygen. In this case, we have a hydrocarbon here. If the thing that you are heating in the context of oxygen is a hydrocarbon, you will always get the two products, CO2 and H2O. Okay, now, there are things such as incomplete combustion and things like that that we'll discuss later. But if we are dealing with a hydrocarbon, which is a compound that's made of hydrogen and carbon, we are always going to get these two products. Okay, so your synthesis reaction to predict your product. Remember, synthesis reactions are going to be characterized by one product, right? So we're going to be taking simpler pieces and combining them to form a single product. Okay, now in this case, we have potassium and chlorine. Potassium is a metal. Chlorine is a nonmetal. When you put a metal and a nonmetal together, you are going to get an ionic compound. So if I have potassium and chlorine and I create an ionic compound, in order to figure out the correct formula, I'm going to use that cross-down method that you guys reviewed earlier. Okay, so remember, potassium has a +1 charge, chlorine has a -1 charge. Okay, you cross those two down, and you end up with KCl as your product. Okay, so notice we have a single product. We don't need to do any reducing down or anything of that sort because of the fact that both subscripts are ones. Okay, now synthesis, remember, is one product. Decomposition is the opposite of synthesis, or the reverse of synthesis. So in the case of decomposition, we're going to have one reactant, okay, and that one reactant is going to break down into simpler pieces. Okay, so in this case, because I'm making you guys predict the products, okay, we're just going to break them down into their simplest form. So if I'm asking you to predict the products for a decomposition process, unless I give you additional information, you're going to assume that it's going to break down into its elemental pieces. So aluminum is going to hang out by itself, while chlorine, its elemental form is diatomic because it's one of the 7 diatomics. Okay, notice we start with one reactant, we end up with multiple simple products. Okay, so you have your progression there. Okay, single replacement reactions, remember, they're going to be characterized by the swapping of elements. So in order to decide where that swap is going to occur, we need to think about the potential charges of products that would form. Okay, so magnesium right now is in its elemental form, so it's not charged. But if it were to form a compound, right, on the other side, it's probably most likely going to form an ionic compound, right? Because a metal, and then I have two metals as my option. Sorry, two nonmetals here as my option in my compounds. Okay, now, we did learn about acids and bases in the past. Typically, we look at our hydrogen in our acid situations as a +1, chlorine as a -1. Okay, and we've kind of looked at those in the past. Okay, so in this context, if Mg is going to form a +2 ion, when it forms an ionic compound, it's going to want to combine with the thing that's most likely to be negative. So in this context, the Mg and the Cl are going to come together to form a new compound. Now, Mg and Cl coming together, we have +2 for our Mg, Cl is going to be -1. Okay, we're going to cross that down in order to get our ionic compound. So we're going to end up with our MgCl2. Okay, and that leaves hydrogen by itself. Now, the elemental form of hydrogen is H2, so we're going to write it like that. Okay, so when we're deciding who swaps with whom, okay, we're going to have to kind of think outside the box in terms of our charges and what compound and elements we should end up with. Okay, now our double replacement reaction or displacement reaction. Okay, again, there's going to be swapping. Okay, positives and negatives are going to want to come together. Okay, so if we look at this in the compound side, we have a +1, a -1, +1, and a -1. Okay, so when these swap with each other, okay, the positive here wants to go with the negative here. Okay, and the positive here wants to go with the negative there. Okay, so what's going to happen is I'm going to get two new compounds. Ag +1 is going to come together with my Cl-. I cross that down. I end up with AgCl. Okay, and then my Na +1 is going to come together with my NO3 -1. We cross those down, and we end up with NaNO3. Okay? We can then check and make sure that our solubility rules give us one of these as a insoluble product. Okay, we know that chloride, whenever it's with silver or mercury or lead, is going to give you a insoluble solid. So we know that this double replacement reaction will occur accordingly. So if we look at these reactions kind of generically, the pieces that we are looking for are all present. Okay, if I have combustion here, I have a hydrocarbon, I have oxygen, those are requirements. Anytime a hydrocarbon is being combusted, CO2 and H2O will be your products as long as it goes to 100% completion. In synthesis processes, you're going to be taking simpler things and creating a singular, more complicated product. Okay, so in this case, we've taken our two elemental forms of our reactants and we have combined them. We know that it's a metal and a non-metal, so we're going to use the cross-down method and their corresponding anticipated charges in order to identify the new product. Okay, decomposition is just the reverse of the synthesis process. Okay, we're going to take that one reactant and break it into its elemental pieces. Okay. Single replacement, again, we're making sure that we are identifying this as single replacement because we have something in its elemental form, something in a compound form, and that's going to give us a new compound and new element. And when we decide where the swap is going to occur or the replacement is going to occur, we consider the potential charges of those species in the compound. Okay, and then lastly, double replacement. Same concept of single replacement. It's just instead of only looking at a single swap, we are getting two swaps. Okay, the positive and the negative from each of the corresponding substances will come together. Because they're both ionic substances, we're going to use the cross-down method to identify those formulas. Okay, and we're going to, of course, check our solubility rules.